The last speaker of today and of the conference is Michael Hermele, and he's going to talk about navigating the Fracton landscape.
All right, thanks very much. Well, it's definitely a pleasure to be here at this conference celebrating Markus's birthday and with all of you. And so I wanted to say a little bit about Markus actually before we start the last talk. So Markus and I actually started at CU at the same time in 2007, but I don't think we met at that time. And I didn't really get to know Markus until I think it was 2018 when we and also Agnes Baudry discovered that we shared some common interests on kind of the physics of, let's say, quantum condensed matter or quantum many-body systems, and we started talking to each other. And it took kind of a couple years for us to kind of learn how to mutually communicate. And only a couple years later do we really start doing some research together. And it led to a very nice collaboration on parametrized quantum systems, which also involved Marvin Chi and Daniel Spiegel, who are both here at the meeting. And of course, Daniel spoke about some of that topic yesterday. And, you know, for me, like all of this really, it had a big effect on my research and the way that I think about science. And I would say now, looking back on it, these interactions kind of transformed me into a mathematical physicist, which I was not before. But Markus knows all of that. So I also want to say something that I think he doesn't know, which is that way back in high school, somehow I figured out, or I decided without really knowing what that meant, that I wanted to do physics. And if people asked, like, what more specifically, what do you want to do? I said, oh, I think I want to work on string theory or maybe mathematical physics. Again, very uninformed opinion. I had no idea what I was talking about. I went to college, I discovered condensed matter physics, and I didn't work on it as a mathematical physicist at all, and kind of forgot about whatever random things I had said in high school. But in large part, thanks to Markus, you know, I've wound up sort of taking a winding path back to where I originally said I was going. So that's kind of a cool thing. So thanks, Markus, for that. I don't think it would have happened without you. So what I want to talk about today is not, it's definitely, you know, it's one of the outcomes of that transformation, I guess. It's not something that Markus has been collaborating with us on, but I hope you'll find it interesting. And it's together with these people. Evan and Agnes are here, and Wilbur and Bowen are two collaborators elsewhere. And most of what I'm going to tell you is work in progress in sort of various bits and pieces. And then there's one paper that's referred to there. So some of you were at the recent UQM meeting in January, and you might have heard me give a similar talk, which has some overlap with this talk. But I tried to orthogonalize it, and a lot of what I'm going to say is different. So I hope for those who were there will be something new for you in this talk. Okay, so let me start with some motivation. So what is Fracton matter, and why do we care about it? So what it is, and I'll elaborate on this. So we're thinking about zero temperature quantum many-body systems, generally defined on a spatial lattice like a spin system, which have some restricted mobility excitations above the quantum ground state. So I'll say a lot more what I mean by that, but that's kind of the one-sentence definition. And why do we care about this? Well, there are a number of different reasons to care about it. And actually, these reasons come from different areas of physics. So some of the early motivations actually came from quantum information. There are motivations coming from thinking about quantum field theory, which led people who focus on some people who focus on high energy physics to be interested in this topic. For me, I think that the most important reason for me is that Fracton matter gives us a new class of quantum phases that lie beyond the existing paradigms of condensed matter physics, and so we have to come up with new ways of thinking about them. Okay, but the second to the last bullet point is also important, actually. The last two are closely linked together, and really this phenomenon of UV-IR mixing has a lot to do with what's new here, and I'll say a bit more about that. So, in condensed matter physics, it's common for someone to hear a condensed matter physicist say, oh, this is a new phase, so therefore you should be interested in it. But maybe new phases are kind of a dime a dozen, and some are newer than others, some are more interesting than others. So in my opinion, these are the most interesting new phases because they require us to change our thinking the most. I think more than anything else in physics, actually. And some people might disagree with that, but I would stand firm that I think it's really the most new thing that's happening right now. And so why is that? The reason is that I think that fracton phases challenge our ideas about how universality should work. And universality is at the heart of condensed matter physics. It's kind of everything we do. And there's a conventional situation which works in a great many cases, even where we might say that there's some unconventional or exotic physics going on. So this conventional situation, it applies to topological phases, where there's still a lot new to discover. And the conventional situation is that we have a physical system, and we like to think about equivalence classes of physical systems, usually in some ways so that we can deform systems into one another without changing some property, like closing the energy gap. So that will give us an equivalence class of systems, and that's called a phase. And within a phase, there are certain universal properties that are shared by all the systems within the same phase. Okay? And we're interested in those universal properties. And conventionally, what we learn is that these properties are encoded within an effective continuum quantum field theory. Originally, we might have a system defined on a lattice, but the effective field theory is not. And these two descriptions are linked together by something called the renormalization group, which you can think of as a way of eliminating more and more degrees of freedom to get to effective descriptions at longer and longer distances. Okay, and what this tells us is that conventionally, the universal properties of a phase are those at long distances at low energies. Okay, and these are often this is referred to with the word infrared or IR. So the universal properties are IR properties. Okay, so what's different in fracton matter? Well, there's a phenomenon called UV-IR mixing, which occurs in other places in physics too, but there's a particular kind of UV-IR mixing. And what this means in fracton matter is that some of the infrared properties, low energy properties, are very sensitive to short distances. And in short distances, we refer to as ultraviolet or UV. So there's a kind of mixing between short distance and low energy properties. And what's particularly interesting about this, so usually if you see something like this in a condensed matter system, you might think, maybe I'm looking at a very fine-tuned model, and I'm not observing generic behavior that we'll see in the real world without working very hard. But the kind of UV-IR mixing that we have in fracton matter is completely robust to fine-tuning, even to perturbations that break arbitrary symmetries. So it survives small changes to a system's Hamiltonian. If the changes are large, eventually you'll destroy the behavior. But this UV-IR mixing that occurs is really a robust thing. And so therefore, it's intimately tied up with understanding the questions about what are the universal properties of a fracton phase. So I'm going to elaborate. I'll give you a couple of examples, more specifically what counts as UV-IR mixing within fracton matter. Okay, and so the upshot of this is that we really need fundamentally new ideas to answer questions like these. What are the universal properties of fracton phases? This talk is really concerned with the first question, some parts of it. And another important question, which I won't talk about, but I think it's an important direction for the subject in the future, is to think about what are effective quantum field theories for fracton matter, and how, in what sense are they effective field theories? How do they encode the universal properties that we find in answering the first question? Okay, so good. So I want to start with an example, kind of a key example of fracton matter called the X-cube model, which was invented by these people because it illustrates a lot of the basic ideas. This is an example of what's called a Pauli code or a commuting Pauli Hamiltonian. So we put qubits on edges of the three-dimensional simple cubic lattice. And the Hamiltonian is a sum of terms, and all the terms commute with each other pairwise. Moreover, every term is a product of Pauli operators. So BC is a product of Pauli X and on the edges of a cube. And then we sum over all cubes. And then there are three different vertex terms, AV, for three different orientations, where we take a vertex of the lattice, and then we take a product of 4 Pauli Z's on 4 of the adjacent 6 edges, and we leave out 2. Okay. It turns out these terms all commute. The CSS, that just means that every term is either a product of X's or a product of Z's. It's a special kind of Pauli code. So models like this are very nice because not only are they exactly solvable because the Hamiltonian is a sum of commuting terms, they have a lot of nice structure that lets us analyze the exact solution and compute many things. And so we know a great deal about this model. Okay. And so let me tell you some of what we know. And I should say many of the examples we have of models for Fracton matter are of this type. They're commuting Pauli Hamiltonians. So there are two kinds of excitations above the ground state. You can either, so in the ground state, the vertex and cube operators all have eigenvalue 1. You can create excitations by making their eigenvalues -1. So you can have a cube excitation where VC is -1, or you can have vertex excitations where you can take 2 of the A's at a given vertex and make them -1. There's a local constraint where the product of these 3 A's is the identity, so you can't just make a single one of them -1. There are 3 types of these vertex excitations that we'll label with a X, Y, and a Z, and we'll call them L, and the cube excitations we'll call F. So the interesting thing about these excitations is that they have restricted mobility in space. So let's take one of the vertex excitations, LZ. So by acting with Pauli operators, we can take an LZ here and we can move it down 1 lattice spacing, and we can keep doing that. So LZ is allowed to move freely in the Z direction. But we can ask, can we move it in another direction? So let's move it down and try to move it over. Well, it turns out that if you do that, you wind up leaving behind an LX. So you can make LZ turn a corner and thus turn into an LY, but you leave something behind. And this is a fundamental thing. It turns out there's not a way around it. So these vertex excitations are called line-ons because they're free to move along 1D lines, but they're not free. Their mobility is restricted in the other 2 directions. And the only way to get one of them to move in a direction perpendicular to its line is to leave behind some other excitation. Or put another way, if you have a Z line-on, there's no local operator, there's no bounded operator that will destroy that Z line-on and move it somewhere off the line without also creating some other excitation somewhere else in the system. Okay.
They don't necessarily come in pairs.
If you want to create these Z line-ons out of the ground state, you have to create them in a pair. Yeah. What about the cube excitations? Well, here's a picture with a single cube excitation. So what you can do is you can destroy this cube excitation on this cube by acting with a Pauli Z and create 3 nearby excitations on the adjacent cubes. And you can keep doing that and sort of playing around. And what you find is that if you take this cube excitation and you try to move it over here, you wind up creating 2 other cube excitations. Okay, and this is true no matter in which direction you try to move one of these excitations. And what this implies is that actually if you have an isolated cube excitation and you have dynamics that conserves the energy, there's no way for the cube excitation to move. Okay, and that's not a consequence of any special symmetry that's imposed in the model, even though the X-cube model has many symmetries. Even if you add generic perturbations to the X-cube model, this will still be true. And so a cube excitation is what we call a fracton. That's the kind of excitation that gives the subject its name. And fractons are excitations that have the property that if you have an isolated one of them in excitation, there's no way for it to move at all without creating other excitations. Okay, So there are linons and fractons. There are other kinds of excitations. If you take a bound state of two cubes like this, loosely referred to as a dipole, this is an excitation that's mobile in the xy plane. You can also take bound states of two linons and get excitations mobiling lattice planes that way. But these excitations are not mobile in the transverse direction. And so we call these excitations planons. Okay, so that's restricted mobility in a nutshell. So let me say something about UV-IR mixing in the X-cube model, which I promised. So one manifestation of UV-IR mixing comes from the ground state degeneracy. So in infinite space, the X-cube model has a unique ground state. One of the things that Markus taught me actually is how to be comfortable thinking about spin systems in infinite space, which is not something that I used to do, but now I'm a convert to that. And actually almost all of this talk is in infinite space. But you can also ask, if you put this system on a finite periodic lattice of size L, the ground state is no longer unique, and there are actually many ground states. And in fact, the ground state degeneracy grows exponentially with the linear size of the system. Okay, this is an unusual property. This is also robust to arbitrary perturbations. And the thing to notice here is that a small change in L changes the ground state degeneracy, right? A change in L by 1, that's kind of, in some sense, that's a short distance change of the system. We're just changing, kind of only growing the system by 1 lattice site. So that's like a UV property in some sense. But the ground state degeneracy is kind of the ultimate infrared property. It's at very low energies. So this you can think of as a kind of UV-IR mixing. And something just worth saying is that there are other fracton systems, for example, Haas's famous cubic code, which I'll mention a bit later, where even more dramatic behavior occurs. And you can change L by 1, and you can change the ground state degeneracy from a very small number to something which is exponentially large L. So that's kind of very dramatic. So that's one form of UV-IR mixing that occurs in these systems. But I want to say more about restricted mobility because that's what I'm mostly going to focus on. So I'm mostly going to focus on the excitations above the ground state of these systems. Let's be a little bit more precise. So the setting that we're thinking about is zero temperature quantum systems. And I always want to think about translation invariant lattice systems with the local Hamiltonian. Okay, so what it means for such a system to be an example of fracton matter is there's at least one gapped restricted mobility excitation above the ground state. And that's something that we can define. So the first thing that we want to define is the set of super selection sectors, which I'll call S. This is also sometimes referred to as the set of particle types or topological charges. And what these are equivalence classes of excitations. So they're equivalence classes of excitations which may differ from the ground state within some ball. And outside that ball, they locally look like the ground state. So these are point-like excitations. And 2 of the excitations are considered equivalent if they're related by the action of some bounded operator, some local operator. Okay, so that's the notion of super selection sector that we want here. There's a single class in S, a single equivalence class of locally creatable excitations you can make out of the ground state. That's the trivial particle type. And all the non-trivial particle types are what we call fractional excitations. Okay. So another comment is that assuming translation symmetry is important in order to talk about mobility, that comes with some disadvantages, but there's a way around those disadvantages, which I'll talk about later. But for now, we just assume translation symmetry. And let me define what I mean by restricted mobility excitations. So when you have translation symmetry, that acts on the set of super selection sectors. So if you have an excitation A and you act on it with a translation, it may be in the same super selection sector, in which case there's actually a local operator that will hop this excitation over by a translation T, or it may be in a different super selection sector. So this would be a non-trivial action of T, in which case there's no such local operator. So Our translation symmetry on a lattice is always isomorphic to z to the d, where d is the spatial dimension. And for any point-like excitation, we can consider the subgroup of translations that don't change its type. That has to be isomorphic to z to the m, because it's a subgroup of z to the d. Okay, so we say that this excitation f has restricted mobility if m is less than d. So essentially, if there are some directions in which we cannot move this excitation no matter how far we try to move it. So this is a table that illustrates this, and it kind of summarizes what we said about the x-cubed model. So in the x-cubed model, there are fractons for which this subgroup is just trivial. Okay, and there are linons where this subgroup is just z. Planons have the subgroup being z squared. The x-cubed model does not have any excitations like this, except for trivial excitations, which are fully mobile with the invariant translation group of z cubed. Okay, so there's also a kind of UV-IR mixing here, which is less obvious, but also important, I think maybe even more important than the ground state degeneracy. And here what I want to say, so a property of the x-cubed model, which you can prove, is that any two cube excitations, while this is kind of obvious, they're related by some lattice translation, and the lattice spacing is a short distance. And what you can prove is that any two cube excitations at different positions are in different superselection sectors. Okay, if that were not true, they would not be fractons. And
So
yeah,
we have many super selections.
there are many superselection sectors. Yeah, I'll say more about that. So the superselection sector of an excitation should really be viewed as an infrared property, even though these are excitations above the energy gap. And one justification for that is that you can rephrase this whole story about excitations as a story about defects, where you never look at excited states, but instead you make local changes to the Hamiltonian and you ask about the kind of ground states you get in response to those local changes. So I won't say more about that, but that's kind of an important point. So this super selection sector really is an infrared property. And the fact that you can move an excitation over by one lattice site, the shortest distance in the problem, and you can change this infrared property of its super selection sector, that's another kind of UV-IR mixing. Yeah, Leo.
So you would say number of superselection sectors are like x-cubed model is extensive.
It's not, it's sub-extensive in a given size L. That's not obvious from what I said. It doesn't have to be the same as the ground state degeneracy, but it turns out that it grows sub-extensively with the volume of a region.
Mm-hmm.
Yeah. Okay, so just to set the stage for what I'll say in the rest of the talk, let me just kind of say what the assumptions that I'll make when I'm making some general statements. So I want to assume going forward that we have an energy gap to all excitations, and that we have only point-like excitations, so we won't consider systems like the 3D toric code where they're extended loops. The only symmetry we'll impose is translation symmetry, which will play a special role. I'll consider bosonic systems, so think about spin models. I'll always be in 3 spatial dimensions, but we can do things more generally. And a very important assumption is that I only want to consider abelian systems. So those are systems where the type of a composite excitation only depends on the types of its constituents. And another way of saying what this means is that the set of super selection sectors is actually an abelian group under this operation of drawing a box around two things and asking what's the type of the composite. And that operation is called fusion. Okay, so S is an abelian group. And as Emil was asking, isn't it large? Indeed, it's infinite in fracton systems, and in fact, it's usually not even finitely generated. But it's countable. Okay, and so I told you about one example of fracton matter, but the situation that we're confronted with, thinking back over the last 10 years of work that many different people did, is that there are actually many more examples. In fact, there's what I like to refer to as the fracton landscape. There's a whole landscape of examples. And kind of the situation that we've been in as a community thinking about this problem for a while is a situation with many examples and few organizing principles with which to understand the examples. Okay, so I'll give you a flavor. This is another commuting polyhamiltonian. It's called the cubic code. It has all of its non-trivial excitations are fractons. It doesn't have any planons or linons or non-trivial mobile excitations. And so that makes it what we call a type 2 fracton order. Okay, and the X-cube model is what's called type 1 because it has some excitations that are partially mobile, lions and planons. Okay, and there's also some fractal geometry hiding here. So if you try to think about what kind of operator you need to create a collection of well-separated fracton excitations in Haas code, it's actually a Sierpinski fractal. It looks kind of like that. I won't elaborate more on that, but there's some interesting fractal geometry lurking here. And this is still just one example. There are many more. I'm not going to tell you about the pretty pictures on this slide or the next slide, but it's just to say that, like, people have come up with many interesting examples and many large families of examples, but not really a framework to fit these examples into. Okay, many examples, but what to make of all that, right? So here's the fracton landscape. Maybe it looks pretty complicated. So what do we need to kind of get our bearings and get oriented in this landscape? Well, one thing that we need is some kind of a notion of phases, right? And it turns out that that's subtle here. And once we have that, there are sort of two things that we like to do as condensed matter physicists. We like to characterize and classify, and they're not the same. And sometimes in my community, people use these words interchangeably, but we shouldn't because they really mean two very different things. So characterization means that we want to find phase invariants, and these are properties that should be the same throughout a system. They're the universal properties of a phase, right? The other thing that we'd like to do is classification, which is some kind of an enumeration. And usually you have to specify some conditions to have a tractable classification problem. And once you've specified enough conditions, and they should be kind of interesting conditions, then you might be able to actually enumerate the distinct possible phases. And I would say that, I won't talk that much about it in this talk, but very little has been understood in both of these directions. In fact, I think that some of the work that I'll just briefly mention that we've been doing, I think it's the first time that any interesting subset of fracton phases has been classified. But I think maybe even more importantly, there are some examples that predate our work that are important, but very few useful phase invariants that help us get a handle on what's going on with fracton phases. So the approach that I want to take is to study the excitations and develop what I'll call an algebraic theory of the excitations, and then use these algebraic theories to try to answer these questions. So I'll tell you a little bit about that. Okay, so this is really an attempt to generalize something much more familiar and something that's actually quite simple. So for two-dimensional systems where we have anyons, and let's say we have abelian anyons, there's a very simple algebraic theory, which is just a pair of two objects, a finite abelian group A, whose elements are particle types, okay, and a quadratic form on that group valued in Q mod Z, and the values of the quadratic form are just the topological spin of the different particles. Okay, that gives us the mutual statistics through a bilinear form. There's some data which also figured in Nikita's talk very prominently. There's also the chiral central charge. It's partly determined by this data, modulo 8, but not completely determined. But our philosophy is that we're really focusing just on the fusion and statistics of the fractional excitations, and we won't worry about data like the chiral central charge. It's not clear if there are interesting properties like that that will be relevant for fracton phases, but at least for now, our philosophy is just not to worry about that. But that could be interesting to think about for the future. Okay, So this is very well understood. We'd like to generalize it. And there's some new ingredients here. So one important new ingredient is that we really need to think about the mobility of the excitations. That's kind of a key interesting property. And it's also true that if you don't think about mobility of the excitations and you just think about fusion, there's not that much to say about S as an abelian group. It's just some infinitely generated abelian group. So it would be isomorphic to like a direct sum of Z2s or something like that. And what do you do with that? Not much, really. So the mobility information is very important. Okay, and how do we handle that? Well, S is our abelian group of superselection sectors. I'll define a quantity called the fusion order, which is the smallest integer such that if you fuse n copies of any excitation together, you get the trivial excitation. This can actually be infinite, and there are interesting examples, but I'm going to focus on the case where it's finite. And so having translation symmetry makes this group into a module over a Laurent polynomial ring in 3 indeterminates in 3 dimensions with coefficients in Zn, where n is the fusion order. And the polynomial indeterminates just represent translations in the 3 directions of space. You can also think of this as the group rate of the translation group. This is really just coming from the fact that translations act on superselection sectors. So what should the theory be, very schematically? It should be a pair where S is one of the elements, and throughout this talk, I'll have a ring R. R is always this Laurent polynomial ring with Zn coefficients. Okay, so I'll have this R module S, and then there's some other data which I'm leaving vague, and somehow that has to do with statistical properties of the excitation. So it would be like this quadratic form for a theory of abelian anyons. And we know from examples that these restricted mobility excitations do have interesting generalizations of the self and mutual statistics of anyons. In fact, even completely immobile fractons can have non-trivial self-statistics, it turns out. But it's been a very challenging problem to package those examples into a nice algebraic package to understand sort of, is there some nice efficient way of encoding all of the statistical information into some object which would somehow be related to this module of superselection sectors. In special cases, we've known how to do that for a while. But actually, in the last part of this talk, we actually have a more general answer to this question, at least for mutual statistics, and I'll tell you about that. Okay.
Can I ask a question?
Yeah.
So, at least for these super solutions that you can think of it, like if I had one fracton, different locations of it, different elements of different super selection set.
That's true.
Right? But is it obvious that like when you now consider more than one fracton configurations, then somehow they're independent, or that creates a whole new set of super selection sets?
So S is, in the X-cube model, S is generated, we would say it's generated by single fractons and single linons.
Okay.
But not all of most of the elements of S are not single fractons, and so they can't be represented as single fractons or single linons. So there's a lot of other kinds of excitations. It's kind of a big, complicated object, right? Which we can describe in the case of the X-cube model and make it seem less scary, but there's a lot of different excitation types.
There's the generators.
Yeah, they're the generators. Yeah. Okay, so there's a lot of directions that I could go from this starting point, but I don't have a lot of time, and I'm just going to briefly tell you about 2. There are 2 things I want to focus on. Okay, so I want to tell you about the question of what we actually mean by a phase, and then I want to give you this answer for what I think is the algebraic theory of mutual statistics. Okay, so as I kind of alluded to, defining phases for fracton matter is subtle, and there are different definitions in the literature, and I don't have time to get into all the reasons for that. And I'm going to try to treat this lightly. So I'm going to give a kind of a definition of phase equivalence, which we could give all the way back at the level of lattice spin systems. So we could go back to, you know, an operator algebra or something like that on a lattice. But I'm just going to focus on this R module S, on the fusion and mobility data in S. Okay. And there's a kind of standard notion of phase equivalence in condensed matter, which basically just we say that the most important idea is that two gap systems are in the same phase if we can find a path between them, continuous path, through gapped Hamiltonians. Okay. There's more to it than that, but as I said, I'm treating this lightly. In the way that I'm talking about it, the standard notion of phase equivalence, if we just impose translation symmetry as a symmetry, what we would normally do, this is just on S, that just gives us R module isomorphism. Okay. So we can do that. That's easy to think about. But there are some serious problems with that. So one big problem is that the essential physics of Fracton matter is robust to breaking translations. So this maybe is not a good thing to do. Another problem is that if you start to think about this, it gives you way too many phases. So you can take the X cube model and you can apply some lattice rotation to it and come up with a different X cube model where your planons are moving in different orientations of lattice planes. And there's actually an infinite number of ways to do that. Or you could shear the lattice a little bit. Those are all different phases under the standard notion of phase equivalence, and they're all distinct. The corresponding R modules are all distinct. However, they all kind of seem the same, and we don't really want to keep track of that distinction. Okay, however, despite these problems, this is a useful intermediate step. This is kind of the starting point, and we'll call the equivalence classes. Here I said I shouldn't say isometry, that's from a different talk, but let's call these equivalence classes translation invariant phases. And it turns out they form a commutative monoid under stacking, where you just basically stick two systems together, but don't couple them via the Hamiltonian. So there's an idea that I call lattice restructuring, which I think solves these problems in an elegant way. So here's a picture of a spatial lattice with translation. This is a two-step process. So the first step process is called coarsening, and it actually goes back to Hop, where we say, let's just forget some of the translation symmetry, and we'll break the Z-cube translations down to some finite index subgroup. So this is just enlarging the unit self. I'm drawing it in 2D, but I'm thinking about 3D. So this is not quite enough on its own. One reason is that if I do this, then it's hard to compare these two systems because they actually have different translation groups. So how do you compare them, really? And there's another step which you can do is to say, let's deform the lattice and do it in sort of a mild way, where the only thing we're allowed to do is deform how translations act on R3 to line up the new translation group T prime with the original one. And we'll get a picture like this. Now, there's a lot more that you can, I've drawn a very simple version of this operation where I just doubled the unit cell and I did a uniform rescaling, but you can do more complicated things. You can pick more complicated subgroups. In this step, you can rotate, you can shear the lattice, all of that is allowed. Okay, and you can model this by an injective group homomorphism from Z cubed to Z cubed with positive determinant. Okay, and this gives you this gives you an operation on modules which we call restructuring by J, and it's really just restriction of scalars. You're just pulling back the module structure along an injective ring homomorphism. Okay, the underlying abelian group of S doesn't change, but the module structure changes. And you can turn this into an equivalence relation. That's too technical, so I'm skipping it. And if you do this in the right way, you get what we call restructured phases, which also form a monoid under stacking. And there are a lot of nice properties. Okay, so one property is that this gives us a way to, we can still talk about mobility of excitations, but we're not really imposing translation as a symmetry, because any particular translation, think about the unitary operator that represents it on a particular system, we're always allowed to remove that symmetry. So there's no particular element of the translation group that we're so attached to that we always insist that is there. So it's better to think about the kind of coarse translation symmetry that we have as a kind of homogeneity condition rather than symmetry. Okay, but it's a nice homogeneity condition that lets us talk about mobility over long distances. There are other nice properties. It eliminates this problem of too many phases that I mentioned. A very important property that I didn't have time to tell you about is that this operation is compatible with the renormalization group in a certain sense. And we also know that this leads to some manageable classifications of Fracton phases, at least in some sense, in some situations. Yeah, Marvin?
We were always thinking about an infinite lattice.
Always infinite, but yeah. Yeah. So I'm going to kind of mostly skip this because I want to have a couple minutes to talk about the very last thing. But I'll just say that the place where we've made the most concrete progress with characterization and classification are Fracton orders where all the excitations are planons. It turns out that these are still interesting because they're not always just 2D layers. And the answer for the classification depends on the fusion order. If the fusion order is prime, the answer is boring. You can prove it's a kind of boring result, but it's not easy to prove that every theory is just decoupled 2D layers. If the fusion order is a prime squared, and let me say he is odd to be careful, it turns out that every theory is equivalent in this lattice restructuring sense to a stack of K theories that I call Shirley-Slagle-Chen theories. Those have been known for a while, actually. That theory was known for a while. And it's essentially the only interesting theory in the fusion order p squared case, because you can prove that everybody is equivalent to a stack of K SSC theories plus perhaps some decoupled layers. And moreover, this integer K, the number of SSC theories, that's a phase invariant. You can also prove that. So this is kind of a Z classification. It's not really, if you pass to the group completion, it's a Z classification. For those in the audience to whom that means something. And there's a similar result at fusion order p cubed. It does seem to get more complicated as you go to higher fusion order. We're not sure just how complicated yet. Okay, so in the last, I think, 5 minutes, I want to tell you a little bit more about mutual statistics in general Fracton orders. So a very important physical principle, which is sort of the beginning of this whole discussion, is what's called the principle of remove detectability. So this is known for a long time. And it's the statement, one way of stating it, is that if you have a non-trivial point-like excitation, so fractional point-like excitation, you can always detect it by acting with some operator supported very far away. Okay? There's no proof of this in general gapped systems, but it's very strongly believed to be true. Okay? And in abelian anyons in 2D, this condition is enough to ensure physical realizability in the sense that, and it's equivalent actually to non-degeneracy of the quadratic form theta. So it's true that any theory of abelian anyons with a non-degenerate theta can be realized by an abelian Chern-Simons theory, which you can then argue is the effective theory for some lattice model. Okay. All right, whereas if theta is degenerate in a bosonic system, there should not be a way, we don't think there's any sensible way to realize that in a physical system. Perhaps with fine tuning, you could maybe do it, but I'm not even sure what that would mean. Okay. But in planon-only Fracton orders, it turns out that this principle is not quite sufficient for physical realizability. Because there are theories where theta is non-degenerate, where the kind of braiding statistics of the planons is non-degenerate, but you can still argue they're unphysical. And so this needs to be replaced with a new principle, which will state this way, which is that every non-trivial excitation can be detected by some detector, and those are the operators that are quote-unquote supported at spatial infinity. So this first part is really just the same with new terminology. But then there's another statement that every detector should detect at least one non-trivial excitation. So all the detectors have to be effective. And we have some evidence for this new principle in planon-only Fracton orders, where in a certain sense we prove that it's a necessary condition for physical realizability. The other thing we did there is in that context, we gave a precise definition of this set of detectors. Right, that's something here that clearly needs a definition, and so it's an interesting question how to define these detectors more general. So for a more general gap system. Okay, not just a Fracton order with only planon excitations. So how can we define these detectors beyond the planon only case? So I'll give you a definition that comes from Pauli codes. And I'll illustrate it within the maybe most familiar, simplest Pauli code, the 2D toric code. And the rough answer is that detectors are infinite products of stabilizers that locally cancel. So the toric code is kind of like the X-cube model. It has qubits on edges of the 2D square lattice. And some of these operators in it are called BP. They're products of Z are along the edges of a square. If you take the product of all the BPs everywhere on the infinite lattice, they all cancel out and you get the identity operator. Okay, but if you think about that infinite product as an object, you can define a set in which you can talk about these infinite products. You can then ask, well, what happens if I truncate it? Then you get something non-trivial always. No matter how you truncate it, you get an operator which is a product of Z's along the boundary of some big square. And what this does is it detects some of the non-trivial excitations of the 2D toric code. Inside, the toric code has anyons, and this detects what's called a M enyon. This is actually this operator that you're left with is an operator that moves around the E enyon of the toric code, and this is actually a manifestation of the mutual braiding statistics between E's and M's. Okay, so I want to tell you what this, I want to kind of give you a definition in a more general Pauli code. You know, in order to do that, you have to have a definition, a kind of nice definition of Pauli codes to work with. And I want to say, kind of advertise, it's not our work actually, but it's some really beautiful work by Blase, Ruba, and Bowen Yang, where one of the things they do is they give what I think is the right definition of a Pauli code. It's a very nice definition. And so I can't resist telling you about it. So they define a Pauli code to be a free R module, R to the 2Q, with an antisymmetric form that should be P cross P to R, and it's just defined by this matrix, just the antisymmetric matrix. And there's a submodule. That's kind of the important piece of data, is the submodule, which has to live inside its orthogonal. Okay, and we're mainly interested in the Lagrangian case where L is equal to L perk. So it's a very simple definition. To orient the physicists in the audience, L is like specifying the stabilizers of the Pauli code, and Q is just the number of qubits per unit cell, and we have n-dimensional qubits. So what you can do in any Lagrangian Pauli code with only point-like excitations, you can identify this module of detectors by thinking about it as these infinite products of stabilizers that locally cancel. And it turns out that this is just something, it has a nice homological algebra description. It's just Tor2 of S, comma R tilde, where R tilde is an R module of the infinite Laurent series. It's not a ring anymore, but it's still a module over R. Okay? And this remote detection, so detectors can act on excitations, is a bilinear pairing between this module of detectors and S, and it's again valued in R tilde.
But can I ask, so the S is not part of the data. The data, it's all on the first.
Well, you can extract S from this data. Yeah, I'm not telling you how to do that, but you can do that. Yeah. Right. The important point, well, I'll make this point in a minute, and then that's the last thing I'll say. But what does this have to do with mutual statistics? This is kind of a point I need to make. So mutual statistics and remote detection are really the same thing. That's the slogan. Mutual statistics equals remote detection. And the reason why is these detector operators can be viewed as processes where you have some excitations moving around. They would kind of create some excitations, move them around in a very complicated way, and then recombine them, all very far away from the excitation that you're trying to detect. In anyons, that is very simple because your detectors are just string operators of individual anyons. So there's actually a bijection between the set of excitation types and the set of detectors. In fractons, that's not true anymore because the way that you move excitations around is very complicated. But the remote detection pairing between detectors and particle types should be thought of as encoding mutual statistics. Okay, so it turns out that in a Lagrangian, so let me just kind of explain how to package this a little bit more. So in a Lagrangian Pauli code, we actually have more than just this pairing between D and S. You can also extract an isomorphism from S to this object SV, which is a certain X one. It's the second X group of S. Okay, so you get an isomorphism, and this isomorphism actually induces the remote detection pairing. And so this leads us to a proposal that the algebraic theory of fusion and mobility and mutual statistics in a general abelian Fracton orders, even beyond Pauli codes, with some other assumptions, is a pair S theta, where S is the module of superselection sectors, and theta is an isomorphism from S to this second X group. Okay, and it's sort of important that we don't include, the Pauli code has a lot of data in it, but a lot of that is non-universal. It's details of how you present a model on the lattice. All of this data it should be universal data, and it's kind of more directly encoding the universal properties of a face. So you can think about this as more closely analogous to this pair A comma theta, which is an algebraic theory of abelian anyon. So there's a lot still to do with this proposal. This is very abstract, but it can be unwound in many particular, more concrete situations. And we're starting to learn some things from that. And so, I think all I can say now is I think there will be more things to come in that direction. Let me just give you a little bit of an outlook. So I really just tried to give you a flavor of what I think are some of the first steps toward making some real progress to characterize and classify Fracton orders. There are a lot of things I didn't have time to tell you about that have already happened, but there's even more left to do that's not been done yet. And just to give a little bit of an outlook, so from a physics-oriented outlook is that I think we'll see a lot more classification and characterization of Fracton orders, especially beyond the case of only planons, including type 2 Fracton orders like Paz code. And as one thing that will mean is that we're actually finding new examples that we didn't know about before, but rather than just adding to the kind of messy Fracton landscape, these new examples are fitting into a developing framework that I think will unify things together. A more mathematically oriented outlook which I think is maybe not so apparent from what I told you, but we're kind of coming to this emerging picture that Fracton orders can more abstractly be described as symmetric spaces in certain derived categories with a duality. And these are ideas that I think have not come into physics at all. And I think it's going to be exciting to see what happens both for physics and possibly for math from the interplay between physics and these kind of ideas in the mathematical literature. But maybe more important outlook to end the meeting with is that I'm looking forward to many more years of fun and stimulating interactions with Markus. So happy birthday, Markus, and thanks everybody.
Thank you for this interesting lecture. So are there questions?
Yeah, actually, I have had a question more or less to the last topic. What comes into my mind is the Topological-Roberts theory of superselection sectors. And if you look at quantum spin systems, toric code, I mean, Peter Nikens has very nicely established DHR type of superselection theory for those. Is there something similar here, and how does it relate to your?
Yeah, so I've thought about that. I've thought about those kinds of questions a little bit. Some with the student Noah Wellickson, who's here in the audience. I mean, I guess what I would say is that you can define a notion. I think there's a very similar notion of superselection sector that applies within, let's say, models like the X-cube model.
Mm-hmm.
There are some differences though. So like for example, in Niken's work, there's always this cone condition which plays an important role in defining the kind of, that's like a selection criterion that defines the kind of states that you want to consider. So I think that needs to be that definitely needs to be replaced. I could give some examples that show that will cause problems. I think that should be replaced with a condition that essentially you want to look at states for which local operators have expectation values that approach those of the uniform ground state as you go out to spatial infinity. And I think that's kind of the physically right condition. Actually, this cone condition always bothered me, and I think it would be nice to prove a theorem that in 2D these two conditions are equivalent. I suspect that they will be. But yeah, I mean, we can talk more about this later, but those are the thoughts I have about it.
This cone condition seems to require mobility, which...
Yeah, it's designed for mobile excitations. Yes. But even for mobile excitations, it's sort of...
Oh, I see. Yeah.
Yeah. It builds in some assumptions that we can't afford to make in this case. Yeah.
So you mentioned the Lagrangian spaces in turn. And I will guess that Lagrangian space will be generated by the terms in your Hamiltonian.
Mm-hmm.
But that's right. Can you prove that that's actually a Lagrangian space, that there are no other commuting elements in the algebra except the terms in...
Yeah, you can it's usually not so hard to prove that in particular examples. Yeah. For example, that winds up being equivalent to exactness. You can construct a chain complex, and that property is equivalent to exactness at a certain point in that chain complex. And so you have to prove the fact that it's a chain complex is really just that the operators all commute with each other, but exactness is exactly the property that you're talking about. It's not always so easy to prove. In practice, actually, a very good tool in practice for proving this is computer homological algebra packages like Macaulay-Etude. Because if you want to show a sequence is exact, that's a good way to...
I want to point out that when you go back to the spin algebra, then you are dealing with the Cartan subalgebra. Mm-hmm. And then you get this Cartan inclusions is another way to approach this commuting projection. For example, KNS states this become a co-cycle on the states of units, and it's a lot of machinery once you can prove that this is a Lagrangian. So it's very interesting. Yeah, I just wanted to make a comment about this UVIR mixing. It's not obvious to me that for fractons that mixing is unique, though maybe more challenging example. In conventional quantum field theories, conventional phases of matter, we often have commensurability that we need to include that's left over in IR from the lattice model. Like, if you want to get a mod insulator, you have to know about the lattice, and, and there's some discreteness or compactness of variables that you need to include. That's a relic of that UV physics.
Yeah, that's
perhaps
there's something like that can be can also take place, but maybe in a more complicated way in fractal law.
Yeah, I mean, so there's a fundamental difference with those situations, which is that in the kind of situations you're talking about, you can always eliminate those phenomena just by lowering the translation symmetry a little bit. So if you want to strictly you don't always want to do that, right? Like a simple example would be, like if I think about Marvin's talk where he talked about Lieb-Schultz-Mattis theorems, right? Like you have a single spin a half per unit cell. That's a UV property that has important consequences for the IR. There's an anomaly associated with it. We might want to preserve it. However, from a certain point of view, you could say, look, that's fine tuning. Like if I don't really want to assume translation symmetry, that's really a fine tuning. And it's not really like an important property that we need to worry about. But in fracton physics, it's different. because even if you coarsen the translation symmetry by some finite amount, you never get rid of the UV-IR mixing. You can't eliminate it that way. So there's something, I think there may be useful lessons for field theories from work that people did thinking about that kind of UV-IR mixing, which, I mean, as you know, like that's actually a topic that's kind of returned to interest again recently, like with some of Meng Cheng and Nadi Seiberg's work.
Yeah.
So I think that work may have some influence here, but I do think there's this is a much I think it's a more fundamentally different and probably more challenging kind of UV-IR mixing to deal with.
Okay, thank you.
Yeah.
Okay, I think it's time to write the session. So before we thank Michael, I think it's appropriate to thank the organizers, which actually amounts to thanking Mike. Yeah. But also IES, Greg, Leo, and Harry.
And how?
Yeah. And so thank you for organizing this wonderful meeting.